What's up guys, welcome back to another video. Today we're talking about Lab 2, motion of a falling object. So the purpose of this lab was basically to observe the motion of something dropped and to then create a computational model of that motion with and without considering drag, and to then compare all three. Some fundamental principles and models I used were Newton's first law, the momentum principle, and the definition of average velocity. The main result that I got was that my computational model that accounts for drag and my observations look almost the same. So now more into the model's equations and assumptions I used. So the first one I used was Newton's first law, which is basically about how an object stays at rest or at constant speed unless acted on by a net force, as well as how an object maintains constant velocity unless acted on by a force. And this later applies to our discussion about terminal velocity. The next one I used was momentum principle, which is basically about how a force can cause a change in motion, as well as the definition of that force, which is delta P over delta T. So I used this to derive my velocity formula. The same thing I did the same thing for average velocity, where I used the definition to derive a position formula. So now into the actual lab. My system was just an ID card of mine, and the surroundings were just the atmosphere. And the initial conditions were that there was a velocity of 0, and the ID card had a position of 0.3184 meters. So now into the details of the experiment. I dropped the card from the top of a ruler, and I recorded the card's motion using my phone at 120 frames per second. And I uploaded this video onto Tracker and did everything that is necessary. And then using the frame rate, I found the time per frame, and so I was able to obtain a position versus time graph, and this is basically what I did in Tracker. So I plotted each point at each frame, and yeah. So into the coding, like I said earlier, I got the velocity and position formula, and I converted that into code, which I applied right here and right here. And then I also updated that position vector, as can be seen right here. The velocity vectors stay the same, and so this model, which does not account for drag, creates this type of motion, which is much steeper than my observation. But this model that I do account for drag, in which I have a proportionality constant of b equals 0.1271, and the drag force equals that constant times the speed squared, and so the net force equals the force of drag plus the force of gravity. This creates a model that's much closer to my observations. And so graphing all three, as you can expect, the computational model that accounts for drag, which is the blue line, is much closer to the red line, which is my observation, than the green line, which is the model that does not account for drag. So some similarities and differences between the observation and the model with no drag is that during the same time, they had a very different path, and so the model that does not account for drag is way off. However, the model that does account for drag over the same time has a path that's really similar. So yeah, some sources of error were that I didn't read the position correctly, because there's a slight blurriness in this video. So as you can see, like right here, I can't even see where the card is, so I had to estimate. And there's the possibility that I didn't place the point at the same place every frame in Tracker. So as you can see, these are kind of like wobbly. So yeah. So to answer the what does it mean question, so which models, if any, predict a terminal velocity? I think the graph that accounts for drag it does predict the terminal velocity, because the position graph is basically linear, which means the velocity is not changing, which is basically terminal velocity. So what does this mean for the net force? Since velocity is constant, then that means there's no acceleration, and therefore the net force is 0. And to answer the what if question, would terminal velocity be the same or different if we threw it down? I think it would be the same, because in the end, terminal velocity only depends on like the drag force equaling the gravitational force, so it doesn't really matter how fast it initially is going. But this does mean that it's faster to reach, because since you throw it down, it'll take less time to accelerate in order to reach that terminal velocity. So yeah.